Thank you, and thank you everyone for joining us this morning. I want to start off by acknowledging my co-authors. Without Molly's help, the field campaign I'm going to talk about would not have happened, and the whole program probably wouldn't have happened if Brian hadn't twisted my arm to write the proposal. So both of my co-authors are very important in this work I'm going to talk to you today. Next slide. I want to start out by acknowledging the funding from the Utah Department of Environmental Quality. I also want to acknowledge the support from the Utah Department of Transportation, and especially Mr. Howard Trexler and Ms. Donetta Ford, who helped me get permission and allowed me to have access to the Perry Port of Entry. I also want to acknowledge Stacy and Brian for helping me match license plates from Utah and Idaho. And I have to acknowledge my wife, who had a major contribution in helping to save the field campaign when we had some problems. She was able to overnight us some documentation and some equipment that we were able to resolve the problems. And I also want to make an acknowledgement to this website that you see here at the bottom. There's a fellow named Jim Monty who collects license plates for a living, and he's had the veracity to put them on the web. And I use this site repeatedly. He has every state, light duty, heavy duty, old, new, every kind of license plate you can imagine. And when you're trying to identify where a truck's from, it's a very important resource. Next slide. So the instrument I'm using today uses a technique that most of you will be familiar with, of absorption spectroscopy. But I thought I'd introduce it briefly. Pretty simple instrument. It has a light source, it's some type of sample cell, a wavelength selector, and a detector. And if you've used a little benchtop spectrometer in your high school or college days, you ran into the Beer-Lambert equation that said if you knew the path length of the sample that you're looking through, you could relate absorbance to concentration. Next slide. So the University of Denver has an instrument that we call the Fuel Efficiency Automobile Test, which is an open path spectrophotometer. This instrument's a dual wavelength that has an IR source and a UV source. We basically cut the benchtop instrument in half. We put the light source on one side of a roadway, the detector's on the other side, and the sample cell is the roadway. Now there's one problem that we have, and that is, if you remember the Beer-Lambert equation, in open path measurements, you never know the path length of the sample that you're looking through. And so how do we deal with that? Well, my former boss, Don Stedman, came up with the idea that the way that you deal with it, especially from vehicles burning carbon fuels, is you make a ratio measurement and you correlate every species you measurement to carbon dioxide. And by doing that, you end up with two Beer-Lambert equations, one in the numerator and one in the denominator. And because the plumes is coming from a single source, the path length is the same for both of those, and it crosses and it cancels out. So the current instrument that we have is capable of measuring CO, hydrocarbons, nitric oxide, ammonia, sulfur dioxide, nitrogen dioxide. Typically, we also include speed and acceleration measurements, and we always image a picture of the license plate so that we can get vehicle information. Next slide. Now, here's what the measurement process actually looks like. In the top graph, I've plotted a time series of concentration for CO2, CO, and hydrocarbons of about a half a second of exhaust behind the vehicle. One of the other differences in feet compared to the standard benchtop instruments is the speed at which the detectors work. Everything's collected at 100 Hertz. And as you can see, as the plume rolls behind the vehicle, concentrations of all three species move up and down together. I've purposely included a high emitting vehicle here so that you can see the CO and HC values move around. And so then when we calculate the molar ratio, we ratio CO to CO2 or HC to CO2. You see the result of that in the bottom two graphs. We get a nice correlation with a straight line. The slope of that line is the molar ratio for that species. Now, it's fairly simple to change that molar ratio into a fuel specific emission measurement. So we end up with grams of CO or grams of hydrocarbon per kilogram of fuel. And those are the values that I'll be reporting in my data today. Next slide. So the idea for making heavy duty vehicle emission measurements in the winter was something that Brian was very much interested in. We've made a number of heavy duty emission measurements over the last 20 years, and almost all of those have been in very warm weather situations. And even recently, there are only a few studies that have looked at heavy duty emission measurements in winter temperatures. And one of the limitations is many of those studies have been near road studies, and they haven't identified vehicle information as a part of those emission measurements. And so that was one of the motives for putting this project together. The measurements were collected at the Perry Port of Entry that's located between Brigham City and Perry, north of the Salt Lake City area on I-15. And we set up our equipment at the exit to the southbound side of that port of entry because the DOT people told us that had the heavier truck traffic. Next slide. So the picture I showed you before was making light duty measurements with have ground level exhaust emissions. And so all the equipment was located on the ground. Heavy duty trucks have both elevated exhaust pipes and ground level exhaust pipes now. And so for the elevated pipes, we have to elevate our sampling beam. We do that by using aluminum scaffolding on the sides of the road. You can see the light source on the other side, the detectors on the nearest picture. What's hard to see is there's a road barrel in front that is our plate camera. And then for this project, we also used a thermal imaging camera to look at temperatures of the elevated exhaust pipes. Next slide. This is another picture just looking at the detector side of the setup for elevated pipes. Because we've elevated the beam actually never gets blocked to trigger a measurement. And so we also have to include a measurement trigger to start the measurement. You can see the speed detectors, the computers and the calibration cylinders that we use are all located inside the motorhome. Next slide. This is just another picture from the front showing you the setup, truck going by with an elevated exhaust pipe. Next slide. As I mentioned, heavy duty trucks also have ground level exhaust. This is something that's relatively new. They didn't start using ground level exhaust in heavy duty trucks till the 2011 model year vehicles. And so most of the newer trucks, there'll be a mixture of ground level and elevated exhaust pipes. And we spent time both with elevated measurements and with ground level measurements. And this is just a picture of after we've moved all the equipment to the ground to do the ground level exhaust measurements. Next slide. So as I said, this was a winter campaign. We collected measurements for 5 days between December 7th and December 11th in 2020. The pictures here at the top give you an idea of what we capture with each of the measurements. The plate picture there is on the left, and the thermal image of the exhaust pipe for this same truck is located there on the right. Over the 5 days, we collected more than 2,200 valid emission measurements. We were able to recover almost 1,800 readable license plates out of those measurements. We were able to match to vehicle registration information all but 100 of those readable plates, which is quite astounding. And the vast majority of those matched plates are the class 7 and 8 heavy duty vehicle measurements. You can see the breakdown in the number of elevated measurements that we have versus ground level. And the temperature range during the measurements for that week went from -7 degrees to 10 degrees C with an average around 4. Some statistics, the elevated exhaust measurements fleet is significantly older than the trucks with the ground level exhaust. And this is in large part, it has to do with the fact that ground level exhausts are only recent in trucks, and that's by and large the differences on the age. Average speed we observed was almost 29 miles an hour. And the plate distribution, the majority, of course, was from Utah trucks, followed up by Idaho and Indiana. But overall, we saw trucks from 37 states and every province in Canada, except I believe the Northwest Territories. Next slide. I'm only going to be able to tease you today with some of the data. We've only had the database finalized for a couple of weeks. And so we don't have a lot of results just yet. But this is a graph of fuel-specific NOx emissions by chassis model year for the Utah measurements that we just completed and a comparison to California measurements that we made 3 years ago. Now, I caution you not to read too much into this just yet, because there are a lot of differences between these two fleets, not the least of which is age, but also the age distribution and even the technology distribution to some extent. But one of the things that will jump out at you, of course, is that the Utah measurements have higher NOx emissions. The mean emissions are about 30% higher than we see in California. And the other thing that'll jump out at you is that in California, starting with about the 2008 chassis model years, we see a steady decline in NOx emissions in those trucks all the way up into the new trucks. The Utah measurements, we don't see that transition occur until the 2014 model year trucks. And then it goes down to about 2017, and 2017 and newer all have about similar fuel-specific NOx emissions. The other thing that you'll notice is that if you look at the 2013 model years and older vehicles, by and large, those NOx emissions for a mean are pretty much the same as you go back in time. And the other thing that you'll notice is that by and large, the older trucks in California have somewhat similar NOx emissions to what we're seeing from the older trucks here in Utah. I should also point out the uncertainties that I plotted here are standard errors of the mean. Next slide. So this is a graph of fuel-specific ammonia emissions versus chassis model year, comparing the same two data sets that I used for the NOx measurements. Now, heavy-duty diesel trucks do not make ammonia as part of the combustion process. It's something that's introduced as part of the aftertreatment systems. So as part of the selective catalytic reduction systems, the trucks inject urea in the front of the catalyst, and that's thermalized into ammonia, and then the ammonia is used to reduce the NO and the NO2. And so you're only going to see ammonia emissions when there's excess ammonia that's been introduced to the catalyst, and there's some left over from the reduction reaction that gets emitted from the tailpipe. And what you'll notice is that for both the California and the Utah data sets, we only see ammonia emissions in these newer trucks that have SCR systems. And they tend to go up as the truck gets newer, and then they tend to decrease as the trucks get older. You'll also notice that I have a slight negative bias on the zero measurement. Some of that may have to do with the noise that gets introduced when we're up on top of the scaffolding. But the other thing you'll notice that by and large, the ammonia emissions between the two data sets in terms of the maximum amounts of ammonia we see are somewhat similar. Next slide. To give you a perspective on how large these ammonia levels are that we see from the heavy-duty diesel trucks, I've also introduced now data that I collected in the fall from light-duty gasoline-powered vehicles. And what you'll notice is that even for the newest heavy-duty diesel trucks, the ammonia emissions that we see from these trucks are about half of what we see from the light-duty fleet for a similar age. And when you look at maximum levels that we see from the light-duty fleet, the emissions we see from the heavy-duty trucks are significantly lower. I'll also point out there's a lot of push now for alternative fuel vehicles, and natural gas is one of those, especially on the heavy-duty side. You'll see in refuse trucks and drayage trucks and a lot of package delivery trucks. By and large, natural gas engines, especially if they're stoichiometric, which most of the new ones are, will emit up to an order of magnitude more emissions than we see from light-duty gasoline vehicles. And that's something to keep in mind if you're concerned about ammonia emissions. Next slide. So finally, I just want to say, anytime you can have a data campaign and you come away with as many measurements we got on heavy duty trucks, you have to call that a success. Doing the measurements in winter was more challenging than what we found in warmer times. And there were some issues that we had to work through, but by and large, we had a very successful data collection campaign. Almost 1,700 measurements. The vast majority of those were from class 7 and 8 trucks. We were able to find a week where the temperatures were reasonably cold and we didn't have any snow events, which would have been an issue. However, as I mentioned before, the analysis has barely begun, And so there will be further results forthcoming, and it's something that we're really excited to look at. So I thank you for your time, and I'll try to answer any questions.
Thanks, Gary. Who has questions?
So Gary, I assume one of the next steps is to look at the emissions as a function of temperature. That would be really interesting.
Yes, and if you've got any ideas, I'm all ears.
No, just having talked to Brian many times, he's quite interested in the temperature dependence. So
well, and part of the issue that we have is that, as I mentioned, the most recent data set I have is from California from 3 years ago, and certainly there's more than a 20°C temperature difference between those sets, but there's also lots of other differences between those sets. So untangling all of those things may be difficult.
It looks like Logan Mitchell, you've got your hand raised.
Yeah, really interesting presentation. Is the lower NOx emissions in kind of from a decade ago between California and Utah trucks, is that related to a change in vehicle regulations in California?
Well, not directly, because the regulations are all the same right now between California and Utah. But California pushes the envelope in getting fleet managers to operate their newest equipment in California. And so one of the things that you have to deal with in California is that the age of that California fleet's always going to be younger than what you see anywhere else across the US. And it's not just because they've done away with the old trucks. It has to do with fleet managers are pushed to introduce their newest and lowest mileage vehicles in California first.
But you're looking at the age of the vehicle from California versus the age of the vehicle from Utah. So that
yes,
the age of the fleet should be accounted for in that.
Yes, certainly when I plot it against model year, that's taken care of. When I'm talking about mean emissions, that's something you have to consider.
Yeah.
We're doing hand raises today, and I figured out I can see him. So John Soul, I think you had your hand raised next. Oh, you're muted though, John.
Yep, thought I unmuted. I have a question about altitude as far as both Chicago and California, depending upon where in California, are fairly low altitudes versus Perry, and issues with running lean or rich. Have you accounted for that?
Not yet. Typically, altitude with these newer systems isn't an issue. The old mechanically operated diesel engines, altitude is something that you have to consider.
Great. We have time for another question. Someone, go ahead, Daryl. And I just want to say before you start, you don't have to raise your hand. You can just start talking. But if you want to raise your hand, that's awesome too.
Hey, Gary, did the trucks have a time to cool down before they were measured, or are they running hot right off the freeway?
No, it depends. There are two lanes at Perry. There's an inside lane that forces the truck to go over the scales. Those trucks have to slow to 3 miles per hour. And then there's an outside lane that they allow the trucks to come through at 20 miles per hour. So they've come off the highway. They've had some amount of time, depending on the queue, that they have to wait to get to the scales. And then once they pass the scales, then they can accelerate and leave the station. So no, they haven't come directly off the highway. It's not something that we can totally manage, but it gives you more of an idea of trucks and how they're going to operate in an urban area, as opposed to being just 60 miles an hour out on an interstate.
Great. Thanks so much, Gary, for your presentation.